Our cosmic address, starting with home. We live in a universe that boggles the mind. Its vastness is almost impossible to grasp, stretching out in every direction farther than we can see, farther than we can even imagine. Yet our journey to understand this immensity begins right here, on our home planet, Earth. It's a small, fragile sphere, a beautiful blue and green oasis in the vastness of space, teeming with life. From the towering heights of mountains to the depths of the oceans, Earth is our cradle, the place where humanity took its first steps. But our curiosity has always driven us to look beyond the horizon, to explore the unknown. Just as our ancient ancestors gazed up at the night sky in wonder, we too are drawn to the mysteries of the cosmos. Our desire to understand our place in the universe is a fundamental part of being human. And so, we begin our journey by venturing out from our home to explore the cosmic neighborhood we call the solar system. As we leave Earth behind and journey outward, we gain a new perspective. Earth, a pale blue dot. From space, Earth appears as a tiny, fragile sphere, a pale blue dot against the vast blackness of space, as Carl Sagan famously described it. This image, captured by the Voyager 1 spacecraft from a distance of billions of kilometers, has become an iconic representation of our planet's place in the cosmos. On that pale blue dot, every person who has ever lived, every civilization that has ever risen and fallen, every story ever told, has unfolded. It's a humbling perspective, reminding us of the shared history and interconnectedness of all humanity. Yet it's also a reminder of our responsibility to care for our planet, for it is the only home we know. Despite its apparent insignificance in the grand scheme of the universe, Earth is a remarkably special place. It's the only known planet in our solar system that harbors life, a testament to the unique and delicate balance of conditions that make life possible. Our planet is a complex and interconnected system, with a breathable atmosphere, vast oceans and diverse ecosystems that support an incredible array of life forms. As we contemplate the vastness of the universe, it's important to remember the preciousness of our own planet. Earth is our only home, and it's up to us to protect it for future generations. Our journey through the cosmos begins at home, with a deep appreciation for the wonder and fragility of our own planet. Our stellar neighborhood, the solar system. Our journey through the universe begins right here in our cosmic neighborhood, the solar system. It's a familiar place with our sun at its center, a star that bathes our planet in light and warmth, making life possible. Around this star orbit 8 planets, each with its unique characteristics, along with a myriad of smaller objects like dwarf planets, asteroids, and comets. Imagine shrinking our sun, a giant ball of hot gas that could hold over 1 million Earths, down to the size of a grapefruit. On this scale, Earth would be a mere speck of dust, about the size of the period at the end of this sentence, orbiting the grapefruit-sized sun from a distance of about 15 meters. That's how vast the solar system is, even on a scale we can try to visualize. Our journey through the solar system takes us past rocky planets like Mercury, Venus, and Mars, each with its own story to tell. We encounter gas giants like Jupiter and Saturn, with their swirling storms and rings of ice and rock. And we reach the icy outer regions, home to Uranus, Neptune, and the dwarf planet Pluto. Each of these celestial objects holds clues about the formation and evolution of our solar system, offering a glimpse into the processes that shaped our cosmic neighborhood. Yet, as vast as our solar system seems, it's just a tiny speck within the Milky Way galaxy. Our sun is just one of hundreds of billions of stars that call the Milky Way home, each potentially orbited by its own collection of planets and other celestial objects. As we venture beyond the familiar territory of our solar system, we enter a realm of even greater distances and more mind-boggling scales. Beyond the familiar, a universe of possibilities. The Milky Way, our home galaxy, is a vast spiral of stars, gas, and dust, a cosmic city teeming with activity. It contains hundreds of billions of stars, spread across a disk so vast that it would take light, traveling at an astonishing speed of approximately 300,000 kilometers per second, about 100,000 years to cross from one end to the other. To grasp the sheer scale of the Milky Way, imagine shrinking our sun down to the size of a grain of sand. On this scale, the Milky Way would be a vast disk, stretching across North America, with each grain of sand representing a star like our sun, separated by vast distances. And within this vast expanse, our solar system would be just one tiny speck, located on the outskirts of this cosmic metropolis. But even the Milky Way, as vast as it is just one of billions of galaxies that populate the observable universe. These galaxies come in a variety of shapes and sizes, from spirals like our own to elliptical galaxies and irregular galaxies shaped by cosmic collisions. They cluster together in groups and superclusters, forming a vast cosmic web that stretches across the observable universe. As we venture beyond the familiar realm of our home galaxy, we enter a realm of truly mind-boggling distances and scales. Our journey through the universe has only just begun, and with each step we take, we gain a new appreciation for the sheer immensity and wonder of the cosmos. Imagine looking up at the night sky and seeing not just stars but entire galaxies, each a swirling island of billions of stars. That's the reality of the universe we live in, a universe filled with galaxies as far as our telescopes can see. These island universes, as they were once called, are vast collections of stars, gas, dust, and dark matter held together by gravity. Galaxies come in a variety of shapes and sizes, each with its own unique characteristics. Some are spiral galaxies like our own Milky Way with graceful arms of stars and gas spiraling outwards from a central bulge. Others are elliptical galaxies, more rounded and smooth in appearance, often containing older stars. And then there are irregular galaxies, their shapes distorted by gravitational interactions with other galaxies. These galactic islands are not randomly scattered throughout space. They tend to cluster together in groups, bound by their mutual gravitational attraction. Our own Milky Way galaxy, for example, is part of a small group of galaxies called the Local Group, which contains about 50 galaxies in total. These groups, in turn, are part of even larger structures called superclusters, vast filaments and sheets of galaxies that form the cosmic web we observe on the largest scales. The sheer number of galaxies in the observable universe is staggering. Current estimates suggest that there are trillions of galaxies out there, each containing hundreds of billions of stars, and each of those stars potentially orbited by its own system of planets. The universe, it seems, is filled with more stars than there are grains of sand on all the beaches on Earth. Our own galaxy, the Milky Way, is a barred spiral galaxy, a vast swirling disk of stars, gas, and dust about 100,000 light-years across. From our vantage point on Earth, located about 2/3 of the way out from the galactic center, we see the Milky Way as a faint band of light stretching across the night sky, a celestial river of stars. At the heart of the Milky Way lies a supermassive black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. This black hole, known as Sagittarius A*, has a mass millions of times greater than our Sun, and exerts a powerful gravitational pull on everything in the galaxy. Our solar system, located in one of the Milky Way's spiral arms, orbits the galactic center at a speed of about 220 kilometers per second. It takes about 250 million years for our Sun to complete one orbit around the Milky Way, a journey known as a galactic year. Since its formation, our Sun has orbited the galaxy about 20 times. The Milky Way is a dynamic and ever-changing place. New stars are constantly being born in vast clouds of gas and dust, while older stars die in spectacular supernova explosions, seeding the galaxy with the elements necessary for life. Our galaxy is a place of immense beauty, complexity, and wonder, a testament to the power of gravity and the evolution of the universe over billions of years. Galaxies are not isolated islands in space. They are constantly interacting with each other through their mutual gravitational pull. These interactions can be dramatic and transformative, leading to galactic mergers, starbursts, and the formation of new generations of stars. When galaxies collide, they don't simply smash into each other like billiard balls. Instead, they pass through each other, their gravity distorting their shapes and triggering bursts of star formation. The gas and dust within the galaxies get compressed, igniting new rounds of starbirth in spectacular displays of cosmic fireworks. These galactic interactions play a crucial role in the evolution of galaxies. They can strip galaxies of their gas and dust, quenching star formation. They can trigger the formation of new stars, enriching galaxies with heavier elements. And they can even lead to the growth of supermassive black holes at the centers of galaxies. Our own Milky Way galaxy is on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy. In about 4 billion years, the two galaxies will begin to merge, their spiral arms intertwining in a cosmic dance that will last for billions of years. Eventually, they will settle down to form a giant elliptical galaxy. Venturing beyond the Milky Way, we encounter a vast cosmic archipelago of galaxies, each an island universe unto itself. Our local group, a collection of about 50 galaxies, is just one small group among billions of others scattered throughout the observable universe. The local group is dominated by two large spiral galaxies, our own Milky Way and the Andromeda Galaxy, located about 2.5 million light-years away. These two galactic giants are surrounded by a retinue of smaller satellite galaxies, including the Triangulum Galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud. Beyond the local group lies a vast expanse of space dotted with countless other galaxies. These galaxies are grouped into clusters and superclusters, forming a cosmic web of interconnected structures that stretch across the observable universe. The Virgo cluster, located about 50 million light-years away, is the nearest large galaxy cluster to our local group, containing thousands of galaxies. As we peer deeper into space, we are looking back in time, seeing galaxies as they were billions of years ago. By studying these distant galaxies, astronomers can piece together the history of the universe and learn how galaxies have evolved over cosmic time. As we delve deeper into the universe, we encounter distances that are almost impossible to grasp. The vastness of space is measured in light-years, the distance that light travels in 1 year, which is about 9.5 trillion kilometers. To measure the distances to stars and galaxies, astronomers use a variety of techniques such as parallax, standard candles, and redshift. Parallax, the apparent shift in the position of a nearby star against the background of more distant stars as Earth orbits the Sun, is used to measure distances to stars within a few hundred light-years of Earth. For more distant objects, astronomers rely on standard candles, objects whose intrinsic brightness is known. By comparing the apparent brightness of a standard candle to its intrinsic brightness, astronomers can calculate its distance. One type of standard candle is a Cepheid variable star, a star that pulsates at a regular rate, with its period of pulsation related to its intrinsic brightness. For the most distant objects in the universe, astronomers use redshift, the stretching of light waves as they travel through space. The farther away a galaxy is, the faster it is moving away from us and the more its light is redshifted. By measuring the redshift of a galaxy, astronomers can determine its distance. One of the most profound discoveries of the 20th century was that the universe is expanding. In the 1920s, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. This observation led to the development of the Big Bang theory, which states that the universe originated from a hot, dense state about 13.8 billion years ago, and has been expanding and cooling ever since. The expansion of the universe is not like the explosion of a bomb with galaxies flying outward from a central point. Instead, it is the expansion of space itself, with all points in space moving apart from each other. Imagine a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, representing galaxies, move farther apart from each other, even though they are not moving through the dough itself. The expansion of the universe has profound implications for our understanding of the cosmos. It means that the universe is not static but dynamic, constantly evolving. It also means that the universe had a beginning, a point in time when everything was concentrated into an infinitesimally small region of space. And it raises profound questions about the ultimate fate of the universe. Will it continue to expand forever, or will it eventually collapse in on itself? As we venture further into the vastness of space, we encounter a fundamental limit to our perception, the cosmic horizon. Imagine standing on the shore of an ocean, looking out at the seemingly endless expanse of water. You can only see so far before the curvature of Earth hides the rest of the ocean from view. Similarly, in the universe there's a limit to how far we can see. This limit is determined by the age of the universe and the speed of light. Because light takes time to travel, when we look at distant objects, we are seeing them as they were in the past. The farther away an object is, the longer it takes for its light to reach us, and the further back in time we are looking. Since the universe is about 13.8 billion years old, the most distant objects we can see are those whose light has taken about 13.8 billion years to reach us. This defines our observable universe, a sphere with a radius of about 46.5 billion light-years, centered on us. It's important to remember that this is just the portion of the universe that we can currently observe. The universe itself is likely much larger, perhaps even infinite, extending far beyond our cosmic horizon. The existence of a cosmic horizon has profound implications for our understanding of the universe. It means that there may be vast regions of the universe that we cannot see, and may never be able to see, at least not directly. It also raises intriguing questions about what might lie beyond our cosmic bubble, and whether our understanding of physics, based on our limited observations, holds true in those unexplored realms. Imagine standing on a beach, looking out at the vast expanse of sand stretching in every direction. Each grain of sand represents a galaxy, a vast collection of stars, gas and dust, separated from its neighbors by unimaginable distances. This is the grand tapestry of the universe on the largest scales, a cosmic sea of galaxies stretching as far as our telescopes can see. The observable universe is estimated to contain trillions of galaxies, each a swirling island universe unto itself. These galaxies are not randomly scattered throughout space. They are arranged in a vast cosmic web of filaments, sheets, and voids. Gravity, the architect of the universe, has sculpted this intricate structure over billions of years, drawing matter together into dense regions while leaving vast empty spaces in between. Within this cosmic web, galaxies congregate in clusters and superclusters, gravitationally bound systems containing hundreds or even thousands of galaxies. Our own Milky Way galaxy is part of the local group, a relatively small cluster of about 50 galaxies. The nearest large galaxy cluster to us is the Virgo cluster, located about 50 million light-years away, containing thousands of galaxies in a region about 15 million light-years across. The sheer number and diversity of galaxies in the universe is a testament to the creative power of the cosmos. From giant elliptical galaxies containing trillions of stars to dwarf galaxies barely larger than globular clusters, each galaxy tells a unique story of its formation and evolution. As we study these distant galaxies, we are piecing together the history of the universe, learning how galaxies have formed, evolved, and interacted over cosmic time. When we look up at the night sky, we are not just seeing stars and galaxies as they are now, we are seeing them as they were in the past. This is because light, traveling at a finite speed, takes time to reach us. The farther away an object is, the longer it takes for its light to reach us, and the further back in time we are looking. Consider the Andromeda Galaxy, our nearest large galactic neighbor, located about 2.5 million light-years away. The light we see from Andromeda today left that galaxy 2.5 million years ago, long before modern humans walked the Earth. When we observe even more distant objects such as quasars, billions of light-years away, we are seeing them as they were when the universe was young, just a few billion years old. This ability to look back in time is one of the most powerful tools astronomers have for studying the evolution of the universe. By observing distant galaxies at different distances, we can create a sort of cosmic time machine, allowing us to study how galaxies formed and evolved over billions of years. Astronomers have discovered that the universe was a very different place in its early history. Galaxies were smaller, bluer, and more irregular than those we see today. Star formation rates were much higher, and the universe was filled with quasars, extremely luminous objects powered by supermassive black holes at the centers of galaxies. By studying these distant objects, astronomers are piecing together the story of how our universe came to be the way it is today. Imagine a giant sponge with its intricate network of interconnected filaments and voids. This is a crude but useful analogy for the large-scale structure of the universe. On the grandest scales, the universe is not a uniform distribution of matter, but rather a complex web of interconnected structures, with galaxies clustered together in vast filaments and sheets, surrounding immense cosmic voids. These cosmic voids are vast regions of space, hundreds of millions of light-years across, that are nearly empty of galaxies. They are the largest known structures in the universe, dwarfing even the largest galaxy clusters. The voids are not completely empty. They contain a sparse population of galaxies, along with intergalactic gas and dark matter. Separating and surrounding these voids are filaments and sheets of galaxies, dense regions of the universe where galaxies are concentrated. These filaments and sheets are like the interconnected strands of the cosmic web, tracing out the paths along which matter has flowed under the influence of gravity. Galaxy clusters, like our own local group, form at the intersections of these filaments, where matter densities are highest. The existence of this large-scale structure is a testament to the interplay of gravity and cosmic expansion. Gravity draws matter together into dense regions, forming galaxies and galaxy clusters. However, the expansion of the universe counteracts this gravitational pull, stretching out the fabric of space-time and creating the vast cosmic voids. The intricate web of filaments, sheets, and voids we observe today is the result of billions of years of this cosmic tug-of-war between gravity and expansion. As we delve deeper into the vastness of the universe, we encounter a profound mystery: the existence of dark matter. This invisible form of matter, which does not interact with light, reveals its presence through its gravitational effects on visible matter, such as stars and galaxies. Astronomers first suspected the existence of dark matter in the 1930s, when they observed that galaxies and clusters were moving faster than they should be based on the visible matter alone. This suggested that there must be some unseen mass providing the extra gravity to hold these clusters together. Similar observations of the rotation of galaxies also pointed to the presence of dark matter. Today, we know that dark matter makes up about 85% of the matter in the universe. It forms a vast invisible halo around galaxies, providing the extra gravity to keep them from flying apart. Dark matter also plays a crucial role in the formation of large-scale structure, seeding the gravitational collapse of matter that led to the formation of galaxies and galaxy clusters. Despite its ubiquity, the nature of dark matter remains one of the biggest unsolved mysteries in modern physics. We know it's there, but we don't know what it's made of. Scientists have proposed various candidates for dark matter particles, but so far, none have been directly detected. The search for dark matter is one of the most active areas of research in physics today, as scientists strive to unlock the secrets of this invisible component of our universe. In the late 1990s, astronomers made a startling discovery that shook our understanding of the universe. The expansion of the universe is not slowing down as expected, it is accelerating. This discovery, based on observations of distant supernovae, implies that there is some unknown force at work, counteracting gravity and pushing the universe apart at an ever-increasing rate. This mysterious force has been dubbed dark energy, and it is thought to make up about 70% of the total energy density of the universe. Unlike dark matter, which clumps together under the influence of gravity, dark energy seems to be evenly distributed throughout space, acting like a sort of anti-gravity, pushing everything apart. The discovery of dark energy has profound implications for the fate of the universe. If dark energy continues to dominate the expansion, as current observations suggest, then the universe will continue to expand forever at an accelerating rate. Galaxies will be pushed farther and farther apart, eventually becoming isolated islands in a vast, cold, and empty cosmos. The nature of dark energy is one of the biggest mysteries in modern physics. Some scientists believe it is a property of space itself, a sort of cosmological constant that Einstein first proposed but later discarded. Others believe it is a new form of energy field, yet to be understood. Unraveling the secrets of dark energy is one of the biggest challenges facing cosmologists today, as they strive to understand the fundamental nature of our universe and its ultimate destiny. Echoes of the Big Bang, the cosmic microwave background. Imagine traveling back in time to an era long before the first stars ignited, when the universe was a hot, dense soup of subatomic particles and radiation. This primordial soup, glowing with the intense heat of the Big Bang, has left behind a faint afterglow, a whisper of creation that permeates the universe to this day. This afterglow, known as the cosmic microwave background, CMB radiation, is a faint microwave signal that comes from every direction in the sky. It's the oldest light we can see, a snapshot of the universe as it was just 380,000 years after the Big Bang. Before this time, the universe was opaque, like a dense fog, with light constantly scattering off free electrons. The discovery of the CMB in 1964 was a landmark event in cosmology, providing strong evidence for the Big Bang theory. It's a testament to the ingenuity of scientists who, armed with theoretical predictions and sensitive instruments, were able to detect this faint signal from the early universe. The CMB is not just a relic of the past, it's a treasure trove of information about the early universe. By studying its properties, such as its temperature and polarization, cosmologists can learn about the universe's age, composition, and geometry, providing clues about the fundamental laws of physics that govern our cosmos. A universe bathed in light. The afterglow of creation. As the universe expanded and cooled in its infancy, a dramatic transition occurred. Around 380,000 years after the Big Bang, the temperature of the universe had dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, marked a profound shift in the universe's properties. Before recombination, the universe was a hot, ionized plasma, with photons, particles of light, constantly scattering off free electrons. This scattering made the universe opaque, like a thick fog. Light couldn't travel freely, it was constantly being bounced around. However, once neutral hydrogen atoms formed, the fog lifted. Photons were no longer constantly scattering and could finally travel freely through space. The universe became transparent, allowing light to stream through it unimpeded. The cosmic microwave background radiation we observe today is the afterglow of this ancient light, stretched and redshifted over billions of years as the universe expanded. This transition from an opaque plasma to a transparent universe filled with neutral atoms was a pivotal moment in cosmic history. It marked the end of the Big Bang's initial fireball phase and set the stage for the formation of the first stars and galaxies. Mapping the early universe. Temperature fluctuations and cosmic seeds. The cosmic microwave background radiation is remarkably uniform, with a nearly constant temperature across the entire sky. However, sensitive measurements have revealed tiny temperature fluctuations on the order of 1 part in 100,000 in the CMB. These fluctuations, although seemingly insignificant, contain a wealth of information about the early universe. These temperature variations reflect slight density variations in the primordial universe, regions where matter was slightly more or less dense than average. These density fluctuations, amplified by gravity over billions of years, served as the seeds for the formation of all the large-scale structures we observe today, from galaxies and galaxy clusters to vast cosmic voids. By studying the pattern of these temperature fluctuations, cosmologists can learn about the properties of the early universe, such as its geometry, composition, and expansion rate. They can also test different models of inflation, a hypothetical period of rapid expansion in the first fraction of a second after the Big Bang, that helps explain the universe's large-scale uniformity and the origin of these density fluctuations. The cosmic microwave background is like a baby picture of the universe, revealing its structure and composition in its infancy. These tiny temperature fluctuations, like brushstrokes on a cosmic canvas, hold the key to understanding the origin and evolution of the universe we see today. In the first few minutes after the Big Bang, the universe was an inferno, a seething cauldron of subatomic particles and radiation. As the universe expanded, it also cooled, much like hot gas cools as it expands. This cooling was crucial for the formation of the elements and the eventual emergence of stars and galaxies. In the first few seconds, the universe was so hot and dense that protons and neutrons couldn't combine to form stable atomic nuclei. However, as the universe cooled below a critical temperature, about 1 billion degrees Celsius, protons and neutrons began to fuse together, forming the nuclei of light elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. This process, known as Big Bang nucleosynthesis, lasted for only a few minutes, but had a profound impact on the universe's composition. It determined the relative abundances of hydrogen and helium, the two most abundant elements in the universe, which in turn influenced the formation of stars and galaxies. The cooling of the universe also paved the way for the formation of neutral atoms. As the temperature dropped further, electrons, which had been moving too fast to be captured by atomic nuclei, began to settle into orbit around protons, forming neutral hydrogen atoms. This marked the end of the plasma era and the beginning of a new chapter in the universe's history. After the release of the cosmic microwave background radiation, the universe entered a period known as the Cosmic Dark Ages. This era, which lasted for hundreds of millions of years, was characterized by darkness, as the first stars and galaxies had yet to form and illuminate the cosmos. During this time, the universe was filled with mostly neutral hydrogen and helium gas, along with the elusive dark matter. Gravity was slowly at work, drawing matter together into denser and denser regions, setting the stage for the formation of the first stars. However, the universe was still expanding and cooling, and the gas within it was too diffuse to collapse easily under its own gravity. The formation of the first stars required a trigger, something to push these gas clouds over the edge and initiate gravitational collapse. This trigger is thought to have been provided by dark matter. Because dark matter interacts only through gravity, it was able to clump together into denser halos even during the cosmic dark ages. These dark matter halos provided the gravitational wells into which the normal matter, the hydrogen and helium gas, could fall, eventually becoming dense enough to ignite the first stars. After hundreds of millions of years of darkness, the universe was poised for a dramatic transformation. Within the dense clouds of hydrogen and helium gas that had collapsed within dark matter halos, the first stars began to ignite, bathing the cosmos in their brilliant light. These first stars, known as population 3 stars, were very different from the stars we see today. They were much more massive and luminous, containing virtually no elements heavier than hydrogen and helium. These stars lived short but brilliant lives, fusing hydrogen into helium in their cores at a furious rate and eventually exploding as powerful supernovae. The deaths of these first stars had a profound impact on the early universe. Their supernova explosions seeded the surrounding gas with heavier elements, enriching the interstellar medium from which subsequent generations of stars would form. These explosions also created shock waves that propagated through the early universe, further triggering star formation and contributing to the formation of the first galaxies. The ignition of the first stars marked the end of the cosmic dark ages and the beginning of a new era of cosmic evolution. It was a time of great change and upheaval, as the universe transitioned from a simple, primordial state to a more complex and diverse one, eventually giving rise to the galaxies, stars, and planets we see today. Our cosmic journey has taken us to the edge of the observable universe, a sphere stretching billions of light years in every direction, encompassing a staggering number of galaxies, stars, and planets. Yet, even as we marvel at the vastness we can see, we are confronted by a tantalizing question. What lies beyond the cosmic horizon, beyond the reach of our most powerful telescopes? The cosmic horizon is not a physical boundary, but a limit to our perception, determined by the age of the universe and the speed of light. The light from objects beyond this horizon hasn't had enough time to reach us since the Big Bang. This means that our observable universe is like a bubble of space and time, centered on us, expanding outward at the speed of light. While we cannot directly observe what lies beyond the cosmic horizon, we can speculate based on our understanding of physics and the properties of the observable universe. Some theories suggest that the universe extends infinitely in all directions, with our observable universe being just an infinitesimal portion of a much grander cosmos. Other theories propose that the universe might be finite but unbounded, like the surface of a sphere, where you could travel in any direction without ever reaching an edge, yet the total surface area is finite. We may never know for sure what lies beyond the veil of the observable universe, but the possibilities continue to fuel our curiosity and inspire our quest to understand the cosmos. As we've ventured deeper into the cosmic ocean, we've encountered mysteries that challenge our understanding of the universe. One of the most profound is the discovery that the expansion of the universe is not slowing down as gravity would dictate, but is instead accelerating. This perplexing observation suggests that there's an unknown force at play, a force that counteracts gravity on the largest scales, pushing galaxies apart at an ever-increasing rate. This enigmatic force has been dubbed dark energy, and it's thought to make up roughly 70% of the total energy density of the universe. The nature of dark energy remains one of the biggest unsolved mysteries in modern physics. Some scientists believe it could be a property inherent to space itself, a sort of cosmological constant that Einstein first proposed but later discarded. This constant would represent a constant energy density throughout space, even in the absence of matter or radiation. Others speculate that dark energy could be a new type of energy field, yet to be understood, perhaps associated with a new fundamental force of nature. Unraveling the secrets of dark energy is a major quest for cosmologists, as it holds the key to understanding the ultimate fate of the universe. Will it expand forever, driven by this mysterious force? Or will the expansion eventually slow down, perhaps even reversing into a cosmic collapse? The universe, as vast and awe-inspiring as it is, might hold even more wonders beyond the realm of what we can currently observe. While our telescopes provide stunning views of distant galaxies and unveil secrets from the early universe, they are limited by the speed of light and the vast distances involved. This leaves us to ponder the tantalizing question, what might exist in the unseen universe, beyond our current cosmic horizon? One intriguing possibility is the existence of vast cosmic structures, even larger than the galaxy superclusters we've observed. These hypothetical structures, such as cosmic filaments or walls stretching across billions of light-years, could be remnants of density fluctuations in the very early universe, stretched to enormous scales by cosmic inflation. Another possibility is the existence of different types of matter and energy, beyond the familiar particles and forces we know. Just as dark matter and dark energy were once unknown, there might be other, even more exotic components of the universe waiting to be discovered. These unknown entities could interact with each other and with known matter in ways we can only begin to imagine, potentially giving rise to new and unexpected phenomena. The unseen universe, shrouded in mystery, beckons us to explore further, to push the boundaries of our knowledge and develop new technologies to probe the cosmos in greater detail. While we may never be able to directly observe these distant realms, the pursuit of understanding their nature will continue to drive our scientific curiosity and inspire future generations of explorers. As we delve deeper into the nature of the universe and contemplate its vastness, we encounter concepts that stretch the limits of our imagination. One such concept is the multiverse hypothesis, the idea that our universe may not be alone but could be just one of many universes coexisting within a grander multiverse. The multiverse hypothesis arises from various theoretical frameworks, including eternal inflation and string theory. Eternal inflation proposes that the rapid expansion of the early universe, known as inflation, may not have ended everywhere at the same time. Instead, it might continue in different regions of space-time, creating a multitude of bubble universes, each with its own set of physical laws and constants. String theory, a framework that attempts to unify all the fundamental forces of nature, suggests the existence of extra-spatial dimensions beyond the three we perceive. These extra dimensions could be curled up in tiny compact shapes, and different regions of space-time might have different configurations of these extra dimensions, leading to different physical laws and constants in each region, effectively creating separate universes. The multiverse hypothesis, while highly speculative, offers a mind-boggling perspective on the nature of reality. It suggests that our universe, vast as it is, may be just one small part of a much grander and more complex cosmic tapestry. While we currently lack the observational tools to test the multiverse hypothesis directly, it remains an intriguing area of theoretical exploration, pushing the boundaries of our understanding of the cosmos and our place within it. Our journey through the vastness of the universe has been a humbling and awe-inspiring experience. We've explored cosmic distances that boggle the mind, encountered objects of unimaginable power and beauty, and grappled with mysteries that challenge our understanding of the fundamental nature of reality. From the familiar planets of our solar system to the distant galaxies at the edge of the observable universe, we've witnessed the grandeur and diversity of the cosmos. We've learned about the Big Bang, the event that birthed our universe, and the incredible journey of cosmic evolution that led to the formation of stars, galaxies, and planets. Yet, for all that we've learned, the universe continues to surprise us, revealing new mysteries and challenging our preconceived notions. The nature of dark matter and dark energy, the existence of the multiverse, the possibility of life beyond Earth. These are just a few of the many questions that continue to drive our scientific curiosity. The quest for understanding the universe is a never-ending journey, a testament to the boundless capacity of the human mind to explore, question, and discover. As we develop new technologies and push the boundaries of our knowledge, we can look forward to even more astonishing discoveries in the decades and centuries to come. Our cosmic legacy, a universe of wonder and inspiration. As we stand in awe of the universe's immensity, a profound sense of wonder and inspiration washes over us. The sheer scale of the cosmos, the intricate interplay of physical laws that govern its evolution, the countless stars and galaxies scattered across the vast expanse of space, these wonders ignite our imagination and remind us of our place in the grand scheme of things. We are a part of this universe, born from the same cosmic material that forged the stars and galaxies. The atoms that make up our bodies were once forged in the hearts of ancient stars, scattered across the cosmos by supernova explosions, and eventually incorporated into the gas clouds that gave birth to our solar system, and ultimately, to us. The universe is not a distant, indifferent entity. It's an integral part of who we are. As we continue to explore the cosmos, we are not just uncovering secrets about the universe, we are also learning more about ourselves, our origins, and our place in the grand tapestry of existence. The vastness of the universe should not make us feel insignificant. Instead, it should inspire us. It's a reminder that we are capable of comprehending things far beyond our immediate surroundings, that our minds can grasp concepts of unimaginable scale and complexity. The universe challenges us to push the boundaries of our knowledge, to explore the unknown, and to never stop asking questions. As we continue our exploration of the cosmos, let us carry with us a sense of wonder, humility, and a deep appreciation for the preciousness of our own planet. For in the end, the greatest legacy of our cosmic journey may not be the knowledge we gain, but the inspiration it provides to create a better future for ourselves and generations to come. The cosmic perspective, reframing our place in the universe. Our exploration of the universe's mind-blowing vastness has taken us on an incredible journey, from the familiar shores of our home planet to the very edge of the observable universe, and even beyond, into the realm of speculation about multiverses and unseen realms. This journey has challenged our preconceived notions, expanded our awareness, and left us with a profound sense of awe and wonder. Standing beneath a star-studded sky, we can easily feel dwarfed by the sheer scale of the cosmos. Our planet, our sun, our galaxy, they all shrink to seeming insignificance against the backdrop of a universe teeming with billions upon billions of galaxies, each containing billions upon billions of stars. It's a humbling realization, prompting us to contemplate our place in this grand, ever-evolving cosmic tapestry. Yet the cosmic perspective is not about diminishing our importance but rather about reframing it. It's about recognizing that we are an integral part of this universe, connected to every star and galaxy by the fundamental laws of physics and the shared history of cosmic evolution. The atoms that make up our bodies were once forged in the hearts of ancient stars, scattered across the cosmos by supernova explosions, and eventually incorporated into the gas clouds that gave birth to our solar system, and, ultimately, to us. We are, in a very real sense, children of the cosmos, our existence intertwined with the universe's grand narrative. This realization can be both humbling and empowering, reminding us that we are part of something much larger than ourselves, a story that began billions of years ago and continues to unfold all around us. A universe of wonder, embracing the unknown. As we gaze out at the vast expanse of the universe, we are confronted not only by its immensity but also by its profound mystery. For all that we've learned about the cosmos, countless questions remain unanswered, tantalizing us with the prospect of new discoveries and deeper understanding. What is the true nature of dark matter and dark energy, the invisible forces that shape the universe on the grandest scales? Do other universes exist, perhaps with different physical laws and constants as the multiverse hypothesis suggests? And perhaps most profoundly, are we alone in the universe, or is there life elsewhere, perhaps even intelligent life, gazing out at the same cosmic wonders that captivate us? These questions, once the realm of science fiction, are now at the forefront of scientific inquiry. Astronomers, physicists, and cosmologists are developing new technologies and theoretical frameworks to probe the universe's deepest secrets, pushing the boundaries of human knowledge. The quest to understand the universe is an ongoing adventure, fueled by curiosity, ingenuity, and a deep-seated desire to unravel the mysteries of our existence. The pursuit of knowledge, however, is not solely about finding definitive answers. It's also about embracing the unknown, acknowledging the limits of our current understanding, and remaining open to new possibilities. The universe has a way of surprising us, challenging our preconceived notions, and revealing wonders we could never have imagined. By embracing the unknown, we open ourselves to a universe of possibilities, a cosmos brimming with potential for discovery and wonder. Each new discovery, each step forward in our understanding, deepens our appreciation for the universe's complexity and beauty. It's a reminder that we are still in the early stages of exploring the cosmos, like children taking our first tentative steps into a vast and uncharted wilderness. Our cosmic inheritance, a legacy of curiosity and exploration. As we conclude our exploration of the universe's mind-blowing vastness, we are left with a sense of profound gratitude and responsibility. Gratitude for the opportunity to live in a time when we can contemplate such wonders thanks to the tireless efforts of scientists and explorers who came before us. And responsibility to preserve and nurture the spirit of curiosity and exploration that has brought us this far, ensuring that future generations inherit a universe ripe for discovery. Our cosmic inheritance is not measured in light years or galaxy counts, but in the enduring human spirit of inquiry, the insatiable thirst for knowledge, and the unwavering belief in our ability to comprehend the universe and our place within it. It's a legacy passed down through generations, from the ancient stargazers who charted the heavens, to the modern-day astronomers who peer deep into the cosmos with powerful telescopes. It's our responsibility to nurture this legacy, to inspire future generations to look up at the night sky with the same sense of awe and wonder that has captivated humans for millennia. By supporting scientific education, investing in space exploration, and fostering a sense of global citizenship, we can help ensure that the quest to understand the universe continues, pushing the boundaries of human knowledge and enriching our lives in ways we can only begin to imagine. The universe, in its vastness and mystery, serves as a constant reminder of the power of human curiosity and our capacity for wonder. It's a legacy worthy of our awe, our respect, and our unwavering commitment to exploration and discovery for generations to come.